All right, hello everybody. Welcome. We're going to talk about the fact that equipment used to be reliable and now it's not anymore. The good old days of, they don't make things like they used to. That's a real thing we've seen for a long time, and we kind of have this idea that equipment is just getting worse and worse and worse as we get more and more technologically advanced. So what goes into that and what do we do about it? So here's a picture of a car. This is a 1980s Mercedes-Benz, and these cars are known for their fantastic track record. Routinely, the 300D gets over 1,000,000 miles. Think about that. This car, routinely with the average user makes it over 1,000,000 miles on its odometer. Is that crazy or what? How much do you expect from your car today? Probably not that much. Is that the same reputation Mercedes has now? Maybe, maybe not. Why are antiques so expensive and so sought after? Yeah, there's a sentimental thing there, but what can you tell me about this old mixer that I found in a cheese shop in Amsterdam? Well, it's belt driven, it's made out of some really solid metal. What all that means is that nobody can break this thing. And that's kind of what we see in all the old antiques. My grandfather's old power drill. This thing will never break because it was made to never break. And then the next one I went to was a much bigger mixer over in the chocolate manufactory. You definitely don't want this piece of equipment to mess up because somebody will probably die. You want to design it so that it cannot break. So moving into a business environment a little bit, if I show up with a briefcase like this, it does what it needs to. It gets my computer or my projector from place to place, and it performs its function. It has some padding, and it allows me to carry it around quickly and keep everything in one place. It's nice and black. It's professional looking. But then what's the difference in this briefcase? It has some padding. It carries my projector or my laptop. It has, maybe a few extra pockets, but it keeps everything in one place and allows me to move my equipment from place to place. But what's the difference in how they're designed? If my black briefcase gets damaged, then I'm going to have to sew it up. It's going to be maybe kind of hard to repair. I'm going to have to put duct tape on it. It looks terrible. The one on the left is going to outlive me. There is no possible way that I can break this really on accident at all, and if I fall off the edge of a cliff, it's going to save my life, possibly. Indiana Jones. This is going to be something people fight over when I'm dead. So we want to take this idea of building equipment and building systems to the max. This is a picture of the submarine I was stationed on when I was in the Navy. This is the Henry M. Jackson, and people might have an idea of naval reactors being a really, really competent technical organization that does all these really awesome things, but it's even better than that, actually. What they do is they design these power production and distribution systems for this 600-foot-long warship, and they put a 24-year-old engineering officer over the watch, the shift supervisor in charge of 19-year-olds, 23-year-olds, running this engineering plant. The Navy has an incredible history of no accidents. Do you believe that could really happen in too many other systems run by that type of person? Probably not. It is possible to design things that people cannot break. What's your perception of quality when you see these words? There's a very particular thing that comes to mind, isn't there? Probably the cheapest product that you can find, made using the cheapest materials and using the lowest quality craftsmanship. And so it's very readily available, they're all out there, but there's a very particular picture, mental image, and expectation for a product that just has this on it. That's the reputation. But then when you see this picture, there's a very different expectation that comes to mind. There's an expectation of longevity. There's an expectation of a quality of craftsmanship and materials that I'm probably going to have around for a very long time. One, because I want to take care of it. Two, because it's just more robust and capable of withstanding normal users. And so we're going to start to talk about this concept of sub-optimization and what's good for a single portion of a company maybe, or a single division within your team may not be good for the entire organization as a whole. So we come to this idea of cost analysis, and we started throwing this in with Secretary of Defense Robert McNamara back during JFK and LBJ administrations. And we said we need to apply cost analysis to every initiative that we come across to make sure that we are not wasting taxpayer money. It's a good outcome, absolutely, that we want to pursue. And so when we apply this metric of minimizing cost while still achieving the objectives, we're going to have to do a trade-off. And so we can buy spending less money with things that aren't money. And what we have to give up to minimize cost is engineering performance. And when we do that, we get exactly what we pay for. We get cheap machines that just barely meet the operational requirements, under the perfect test stand conditions. And so now, I've met the requirement and I've minimized the cost, but when this piece of equipment hits the real world, and I don't have those perfect conditions, I don't have 30-year expert operators using that equipment, shocker, it breaks very quickly. And so this idea of minimizing upfront cost is a losing strategy, because you're essentially mortgaging your future operations, your future reliability, to minimize your upfront cost. What you want to start looking at doing is minimizing the total life cost. And this includes, yes, maintenance. This includes your operational schedule. This includes the cost of replacement parts. But you want to start taking your equipment reliability into the mix, because your biggest expenditures, your biggest unplanned expenditures, are going to be lost operational time that you didn't plan for. When that equipment breaks, that's your biggest loss of revenue. That's when we really start to panic. That's when we start to die as a company. Because equipment is expendable, but operations is not. We want to be very careful in the EPC stage, because we can very easily put ourselves in a position where there is no safe way to operate the equipment, because it is so low quality, it is so poorly installed, it is so poorly managed or maintained that we can't keep it going. So when we minimize costs, yes, finance does awesome. They meet their metrics. Our profits look really good for this year. But in the end, the overall system, the company, loses, because our largest expenditure is unplanned maintenance time or unplanned downtime for our operations. That's what we really need to prevent. And when we're only pursuing minimum upfront cost, that's when total life cost goes way up. So we want to caution our leaders and our executives and our decision makers, our planning team and our design engineers. We don't want to accept the mistaken notion that we can just upgrade the plant once we get it running. This is a very dangerous thing. And if you want to take a mental picture of what this might look like in the operational world, if I try to take a Corvette and make it into a safe, usable, efficient school bus, I can't do that. I can't do that and still make money. I can't do that and be reliable. And so I have to design in the reliability to my system to get the outcome that I need. And so we want to take a little bit broader look at our system. What is the system that we're trying to manage? And this is probably one of the most basic things that we learn in life, cause and effect. But how this works in systems and design and equipment is that your system or your machine or your component is producing exactly what it's capable of, nothing more and nothing less. So design intent, your intent, doesn't matter to your machine. All it cares about is its inputs, and that's really all that it can do. It's not some sentient being that's making mistakes. There's just inputs, things happen in the system or the machine, and you get your outputs. There's not really any simpler system diagram here. Okay, so most of the time when we think about equipment failure or reliability, we think, okay, I have a plant, that's my input, and I have my outputs, and the system I'm looking at is the operations, the people that are running it. That's the system that we think of a lot of times when we see a failure. And we think, yep, my inputs are my design, my maintenance, my installation, and my outputs are either failure or reliability or some mix of those two. Well, guess what? That's wrong. That's not the system you are analyzing. That might be your operational team, but if you're looking at a plant or you're looking at a machine, there is much more to it than this. And this is actually a false model. But this model, this mental model, is where we go when we see an equipment failure. All the focus and blame goes where? The operators. Human error. So do any of these ones sound familiar as first root causes that we find? Oh, training, procedures, and supervision. It was just a human error and we need to improve our enforcement. We need to hold people more accountable. And then, once we get past that first level, if that's all we ever do, then, shocker, we're going to have many, many more failures, repeat failures of the same type, because we probably don't have those problems there, or at least that's not all of our problems. The larger companies that have a little bit more oomph behind their fix-it budgets, they're going to start looking at things like rewriting our policies in a global manner. Really making our pre-job and post-job briefings stronger so that we catch every possible hazard beforehand. And of course, our hazard assessments are a part of that. But at the end of the day, all of these corrective actions here are mostly looking at how can we force our operators to do the right thing. But really, when we look at it, our operators are the last link in a long chain of failures that led to this equipment failure. And so we need to start looking more broadly at our model. So for an output, we're still going to have either failure or reliability. It either works or it doesn't. But our system itself, if we're going to look at and really solve equipment reliability issues, we need to include the design, the installation, the fabrication, the maintenance, and the operations. Because that contains many more of the failed safeguards that allow a piece of equipment to fail. And our inputs become that intent and the vision that drives how we build our plant. The amount of funding that we have to do that plant. Yes, that is an input. The proper people that we put on the job to do not just the operations, but the design, the maintenance, and the installation, as well as the time that we give them. And so we just don't want to become too focused on little portions of our expanded view of the system. But most of the time, before we even want to go off to any of the modern technologies, we need to realize that most equipment failures are due to just a lack of executing the basics of taking care of and running machines. And when we have a machine failure and we're only looking at operations, most of the time we see that those repeat failures are a result of just trying to find that quick fix, that easy corrective action that gets us out of the situation and lets us move on with our life, gets ops back up and running, right? instead of thinking about and properly engineering thoughtful solutions to the whole problem that includes the design and installation and maintenance. So one of the ways we can start looking at that is just bringing in our design engineers to the process. One really good business practice I saw recently reading a Heinz Block book. If you have your operations engineer and your maintenance engineer, or your design engineer, as you're building your projects, you say, all right, you guys have your roles. You guys or girls have your roles. You're going to be executing them for a while, and then after an unspecified amount of time, you're going to switch roles. And you can see those incentives and those motivations start to shift. My design engineer now thinks, I'm going to have to run this plant. I want to make sure that it runs right and go out and talk to people. My operators now think, I want to make sure this equipment doesn't break when I'm operating it. I want to operate it properly because I'm going to have to maintain it. You can go to the next level of Navy submarines where operations and maintenance are the same people. So then this is how you can start to get away from this idea of just getting operations back up and running to real reliability. And if we don't do this, if we're only focused on operations, getting operations back up and running, or just blaming the human operator, this is how you see something like a major refinery failure where we go back and do a CSB investigation and find that over the last year we've had 23 failures. Mean time between failures, 2 weeks here. That's pretty terrible. But when we go back and look, our equipment reliability program was chop and swap. Oh, the pump failed, replace the pump. And we didn't do any maintenance or preventive measures. And so that sounds like a terrible idea when we say it here in a nice, comfortable room, but when I'm losing $700,000 a day when my plant goes down, most of the time it's pretty attractive to just replace that pump. But just looking at this list, how much money did we have to spend to fix each one of these pump failures? If we would have just understood what caused the first one and looked at the broader system that includes maintenance and design and installation as well, we'd probably find that there's some other issues there than just my pump keeps failing. And so when we see a repeat failure or a repeated mistake, we need to start internalizing this idea that it's not acceptable. A repeat failure is a decision. And these repeat failures tell you one or both of the two things following. Either we didn't understand the problem the first time, very possible, or somebody did understand the failure and chose to do nothing about it. Was operator fatigue an issue? Was pipe strain an issue? Did we properly mount our pump on a right pedestal? Did we properly store our bearings in a lubricated condition, or did we just leave them out in the middle of a field? Happens more often than you think. So these are the only two reasons why you have a repeat failure. Either you didn't understand the problem in the first place, or you knew that there was probably more going on, and so that we didn't rock the boat or we could just get operations back up and running, we decided to only look at the easy stuff, the procedures, the training, the operator discipline maybe. And so we have all of these basics of maintenance and operations missing, and now we're in the modern world and we're trying to jump to the Internet of Things and automating everything. We have artificial intelligence that gathers all of our data, and we have test points on every piece of equipment at every stage. But automation does many, many wonderful things in the world and makes sure there isn't a human involved so a human can't make mistakes. But automation and electronics and all of these things do have their limits. They have wonderful uses within a certain realm. So our founder, Mark Paradise, had a conversation with Jens Rasmussen a while back. They were just out having lunch, and Jens drew out this table. If we're going to automate a process, we have to make sure that we keep that process in a very, very narrow range. Because the more and more we automate our process, the smaller the deviation has to be that kills it. And so all of our manual processes that we used to have, we didn't have any electronic controls before electronics, they were very robust over a large range of operational conditions. But that didn't get us gigantic efficiency, but it did make it good enough. That's how my grandfather's drill was designed. But we start throwing in, one, all the cost analysis stuff, but two, all the electronic controls, the dynamic stabilities, all of the extra test points and places where it can fail. That means one small change in my system can completely make it fail. So we want to be careful with automation. And what this graph is really telling us is that if I don't have my basics down, automation isn't going to bring too much value, and really it's most likely going to buy me into a lot of extra failures, a lot of extra downtime that I didn't expect. So as professional problem solvers, as we're moving into equipment reliability, there are some things we need to look for. So what is a professional problem solver supposed to do in the maintenance realm? They need to prove the failure mode. I cannot stress enough how important it is to understand how your equipment failed before you try to fix it. Because if you don't understand it, you have no chance to fix the problem, and you're only guessing. So if all we're doing is brainstorming, if all we're doing is just replacing the machine that failed before understanding how it failed, you're probably going to see those 23 pump failures happen over the next year. And you need to look beyond the component that failed. If my temperature and pressure are so high in my fluid system that it corrodes my carbon steel piping, sending all of that grit into my pump fails and I keep replacing my pump and I keep replacing my pump, my failure has absolutely nothing to do with the pump. The pump is running exactly as it should. I'm feeding things from upstream into the pump that are making it fail. So unless I understand how the pump failed and what is causing the pump to fail, replacing it is going to buy me into the same situation. And don't just limit your investigation to material aspects. Doing our chemical swipes, doing metallurgy, doing lubrication analysis. We need to look at everything that pump may be connected to. Its electric power supply to the motor, any electronic controls, any sensors that are there, the piping that it's connected to, obviously the humans operating it and maintaining it and that installed it. So really we need to move to investigating what allowed the failure. And so we troubleshoot backwards from the symptom that we see at the machine to the failure mechanism. If you don't understand the what, how the equipment failed, you will never be able to find out why. But a lot of times what we see is we need to get operations back up and we just jump straight to why and guess at the solution, make an educated guess at the solution, and hope for the best. But that's how we see repeat failures. And so what we need to look at doing is providing objective quality evidence, that OQE, and prove exactly how our equipment failed. That is the point where you can do a proper root cause analysis. And so, in Taproot, in Equifactor, we have a whole bunch of tools for how to properly do that and structure that. But if you see in our first two steps here, these are the what. You can never make a decision on the why until you understand the what. And so we have many, many tools to do that, troubleshooting with Equifactor tables. There's quite a few tools that we want to choose from tables to, what's different this time, or what's different from the rest of my equipment, to the path to failure. How could it possibly physically fail? After you choose the tool, develop a troubleshooting strategy. Many fewer teams than you think develop a strategy on how they need to gather their evidence, and they end up losing most of it. And then we just have to make that educated decision. You need to troubleshoot intelligently, so you do it in the least amount of time while properly gathering your evidence. And then once you have all of the understanding around how the equipment failed, retaining all your evidence, you understand what led up to the failure and what allowed the failure, then you can build a snap chart and do your root cause analysis. So all of those Equifactor tables come from equipment reliability expert Heinz Block. I partnered with him back in the 1990s. All the failures that he saw while troubleshooting oil and gas equipment all over the world, we have tables. Every possible failure that a pump or a compressor or a transformer in your electrical system could experience, they're all right there. And then all of your possible causes for each of them, they're listed. This doesn't become a replacement for your equipment troubleshooting experts, your operations, your maintenance people. This becomes a tool to structure their brainstorming and to move through the process of troubleshooting very, very quickly. Again, if we're losing $700,000 a day, every minute we save, money in the bank. So, we'll take a quick look at the troubleshooting tables, what those look like. So here we have, under pumps, centrifugal pumps. Here's all the possible things that can go wrong with a centrifugal pump. But in a situation where I had a failure, I only care about the symptom I'm seeing, so I get rid of everything else here except for that green check mark under short mechanical seal life, because that's the problem that I'm seeing. There's only so many possible causes for that symptom. But instead of putting all of my experts in front of a blank whiteboard to brainstorm all of these things or to fault tree it or to cause and effect it, here's everything it could possibly be. Now let's get rid of everything I don't care about here or that I haven't seen or that I've already proven that isn't the case. There we go. There's really only a few things that we don't know. Now we build a troubleshooting plan around these and we can go out and fix them. I guarantee you your experts will move through this way quicker than a brainstorming session because it's all right here. Here's your procedure to troubleshoot short mechanical seal life. Easy day. So, I have this extra Whamodyne piece of equipment that nobody's ever seen before. There's no table. Build one. Maybe I have my old best refrigeration plant that only Joe knows how to run. Build a table with all of his knowledge. If you know all of the industry best practices, this is a good place to tabulate them. Also, if I have a brand new mechanical engineer right out of college that doesn't really even know the difference between a pump and a compressor, this is a really good way for them to train up and start accumulating and assimilating all of that 30-year expert knowledge without losing his own blood, without putting in his own sweat and his own painful experience. Now he knows what to look for. So, you want to take all of your failure modes and effects analysis, your engineering has probably already done this, and be proactive. Build an equipment troubleshooting table just like we saw, and now all of that proactive kind of theoretical analysis now becomes a troubleshooting and fixing tool that I can hand to my maintenance and reliability teams. So, how do we learn how to do all this? There's a whole bunch of places that you can learn how to build equipment troubleshooting tables, how to use them for Taproot root cause analysis. Taproot.com/Equifactor. Look at the Equifactor books. Come to a 2-day Equifactor troubleshooting course. Come to the equipment reliability track at the Taproot Global Summit. Easiest ways to contact us at System Improvements to learn more about Equifactor. So I hope you learned something today about why equipment isn't reliable anymore and some of the things that we can do to move in a direction of reliability. And maybe we've learned a couple steps in how to broaden our thinking, but also how to troubleshoot equipment in an objective and evidence-based way. Thanks a lot. Let's go make equipment more reliable.